In this video, we demonstrate that it's possible to analyze cardiac pulse from regular videos by extracting the imperceptible motions of the head caused by blood flow. Recent work has enabled the extraction of pulse from videos based on color changes in the skin due to blood circulation. If you've seen someone blush, you know that pumping blood to the face can produce a color change. In contrast, our approach leverages a perhaps more surprising effect. The inflow of blood doesn't just change the skin's color, it also causes the head to move. This movement is too small to be visible with the naked eye, but we can use video amplification to reveal it. Believe it or not, we all move like bobbleheads with different motions at our heart rate, but at a much smaller amplitude than this. Now you might wonder what causes the head to move like this. At each cardiac cycle, the heart's left ventricle contracts and ejects blood at high speed to the aorta. During the cycle, roughly 12 grams of blood flow to the head from the aorta via the carotid arteries on either side of the neck. It is this influx of blood that generates a force on the head. Due to Newton's third law, the force of the blood on the head equals the force of the head acting on the blood, causing a reactionary cyclical head movement. To demonstrate this process, we created a toy model using a transparent mannequin head with rubber tubes stand for simplified arteries. Instead of pumping blood, we will pump compressed air provided by this air tank, and I can release the air using this valve. Now watch what happens as I open and close the valve once a second, similar to a normal heart rate. Ready? Here. This motion is fairly similar to the amplified motion of real heads that we've seen before. We exploit this effect to develop a technique that can analyze pulse in regular videos of a person's head. Our method takes an input video of a stationary person and returns a one-dimensional signal corresponding to the head motions. From this signal, we can extract an average pulse rate as well as beat locations for deeper clinical analysis. We begin by locating the face using a face detector and selecting feature points within the area. The feature points are tracked from frame to frame of the video using the Lucas-Canati tracking algorithm. We use the vertical or Y component of each of the feature point trajectories for our analysis. Next, we temporally filter the signals to a passband encompassing a normal pulse range while excluding extraneous motions like respiration. We decompose the multidimensional motion of the head described by the trajectories into submotions using principal component analysis or PCA. PCA returns the main directions along which the head moves. We project the motion of the head onto each component and choose the signal with the clearest dominant frequency. We use the dominant frequency to obtain an average pulse rate. Finally, we perform peak detection on the chosen signal to obtain beat locations for further analysis such as heart rate variability. We tested our method on different people varying in skin tone and gender and were able to get nearly exact pulse rates compared to an ECG device. In addition, our method produced similar beat length distributions to the ECG, an exciting result that shows that we can capture more subtle information about the heart than just an average rate. Finally, our method is robust to different views of the head. We obtained a pulse from a sleeping newborn, from the back of a subject's head, and even when a person is wearing a mask.